Hello everyone, once again welcome to the channel Chemistry Classroom Teaching Videos. In this part 3, I will discuss the splitting pattern of d-orbitals in presence of the octahedral field, square planar field and square pyramidal field. Those who have not yet watched the earlier videos, I will request you please go to the channel, and here I have written the name of the videos. Please watch them first, then follow this video. Now see. In an octahedral field, that means this is my field. Yeah. See, I can consider this as x, y and z axis. Okay. I can consider, here I know that coordination number of the metal is 6. I am considering the metal at the center and the 6 ligands are approaching the metal. See, these dots represent the ligands. These 6 ligands are approaching the metals all along the coordinate axis. Now what will happen? Obviously the metal d-orbitals which have lobes directly along the coordinate axis. That means which two orbital? You all know, I know that dx square minus y square and dz square. These two orbitals only have lobes along the coordinate axis. So they will be repelled strongly by the ligand field compared to the other 3 orbitals, that means dxz, dyz and dxy, and thus they will be stabilized in order to maintain the barycentral rule. So the splitting pattern in octahedral field will be somewhat like this. If I consider this as the free iron d orbital, then obviously here dx square minus y square and dz square will be energized in compared to the other 3 dxy, dxz and dyz. They will be stabilized. Now see, these are threefold, so I am calling it as T2G and these are twofold, calling it as EG. Here G stands for geometry, even that means these field, these geometry have a center of symmetry, so I tell them G, but in the earlier one, tetrahedral, they lacks the center of symmetry, so they are only T2 and E. Now here also, like before in tetrahedral field, these energy difference between the T2G and EG set of orbital is represented by 10 dQo or del O. Okay? And these extent of energization will be, this will be plus 0.6 del O or plus 6 dQo, and these extent of stabilization will be minus 0.4 del O or minus 4 dQo. Okay. Now see, these are the parameters del O, which represent the energy difference between the T2G and EG set of orbital for octahedral field, and earlier we have seen del T, which represent the crystal field splitting in tetrahedral field. Now this is a common question, that why del T is less than del O. Can you tell me why del T is less than del O? See, in tetrahedral field, what's happening? 4 ligand, only 4 ligand is approaching the metal ion. So obviously the electrostatic field generated by the 4 ligand will be lesser compared to the field generated by the 6 ligands which will be approaching in the octahedral field. So obviously here in the tetrahedral field, the crystal field splitting will be lesser in compared to the octahedral field. And another more important thing is also present. What? In the tetrahedral geometry, what we have seen? That none of the ligand, none of the metal d orbitals directly faces the ligand. All are in between. Some are more closer to the ligand, so they are energized. Some are further from the ligand, so they are stabilized. But in the octahedral field, 2 orbitals directly faces the ligand negative charges, dz square and dx square minus y square. So they will be repelled much more strongly. So obviously the crystal field splitting in octahedral geometry will be much much more than that in the tetrahedral geometry. Now let's move to the next geometry, that is square planar. See, what is square planar? I can think like this, that this is a square, okay? You know, I have already apologized that I am not at all good in drawing, so please forgive me for this thing, okay? No, I have to erase it, it's very bad. Okay. See, if I consider a square planar geometry like this, that is at the four corners of a square, I have placed the four ligand and the center the metal. Now obviously this is my z axis. Now see, can you find any similarity between the octahedral geometry and the square planar geometry? Now see students, if I place two more ligand along the z axis, what will happen? Tell me what will happen? It will be an octahedral geometry. So we can think like this, that if the two ligands in the z direction is pulled out, that means z out distortion. Actually we are pulling out the ligands in the z direction, plus z minus z. Then the z out distortion of an octahedral field will lead to a square planar geometry. So obviously what we can think, that the splitting pattern present in the octahedral field, over there the z component, that means the orbitals having z component, will be rippled less now here in the square planar geometry, and they will be to some extent stabilized. So see the splitting pattern. This is for the free ion. Okay. First let me draw the octahedral one. You know this is dx square minus y square and dz square. And this is obviously what? dxz, dyz and dxy. This is in octahedral field. Now z out distortion leads to the square planar field. So obviously if I do z out distortion, what will happen? My dx square minus y square will raise somewhat and dz square will be stabilized. Okay? It will be lowered. And here, over here also what happened? Since here the ligands are present in the xy field, xy plane, so obviously the orbitals containing the xy plane will be repelled much more strongly. So in compared to these three, these dxy will now raise in energy. And it will raise to such an extent that it will go up dz square. Here I will have dxy and the other two will remain the same. dxz, dyz. So this is the picture of a square planar field. Hope you all get it. No need to remember the splitting pattern. Just apply your logic. You can draw it by yourself. Okay. Now move on to the last geometry. Square pyramidal geometry. Square pyramidal geometry. See, over here what I can think, I am once again drawing the square planar geometry. Y, X and my Z axis. Already in square planar these four ligands are present. Here coordination number is 5, you all know. This is the metal ion. In addition to the square planar, what's happening? A ligand comes over here in the plus z direction. So what difference it will make? Obviously now you can see that the metal d orbital which have low directly along the z axis will be repelled much more strongly in compared to the other ligands. So in addition to the square planar field where we have seen that dx square minus y square have the highest energy, here also the dz square, because here in the z direction I have one ligand only. So dz square will also be energized, but its energy will be little less than the dx square minus y square, because here in the z direction only one ligand is approaching. Okay, so what will be the splitting pattern? Let me show you. If this is the energy diagram, this is the free ion, then what will happen? dx square minus y square will be highest. It will be most energized because it will be strongly repelled because all the four ligands are in the xy plane. But in addition to that, dz square will also be energized. Okay? And dxy will be stabilized, but it will be more repelled than dxz and dyz. Okay? So the energy of dxy will be greater than these two orbitals. Now a question you may arise that, ma'am, why dxy is not with this? It's very simple, because you know that in dxy orbital, the lobes of the orbital are in between the axis, not along the xy axis. But in dx square minus y square, the lobes of the orbital are along the axis. So obviously it will be highest energized, then come dz square because I have one ligand along the z-axis, then come dxy, then come the other two. So this is all about the splitting pattern of metal d orbital in various geometries. Hope you understand this chapter, and it's my humble request to all of you, please do not mug up or memorize this splitting pattern. You all please try to do it by yourself after watching this video, after reading the textbooks where this topic is written. Please go through the textbooks also, and then you just try to draw it by yourself. It will boost your confidence. Okay? Thank you for watching the video.